안녕하세요. 저는 서울대 수리과학부의 류경석입니다. 저는 이제 수학자로서, 응용수학자로서 최적화와 그리고 머신러닝에 대해서 연구를 하는데요. 그래서 머신러닝에서는 이제 우리가 흔히 의인화해서 부르는 이제 훈련이라는 표현이 사실은 최적화 문제를 푸는 것이잖아요. 그래서 저는 이제 최적화 전공자로서 이제 딥러닝 시스템의 어떤 그런 훈련 과정에 대해서 이제 이론적으로 연구를 하고 있습니다. 그래서 오늘 이제 발표드릴 주제의 제목은 Training Dynamics of Complexity of Infinitely Wide WGAN and Minimax Optimization 이라는 주제로 오늘 발표 제목을 준비를 해보았는데요. 사실 이번에 이제 이번에 퍼블리시한 논문 두 편을 이제 어느 정도 플레이버가 좀 달라서 두 가지를 이제 하나씩 말씀드리고자 합니다. 그리고 발표는 영어로 준비하여서 이제부터 영어로 발표를 진행하겠습니다. So good afternoon, and thank you for coming to my talk. So the first topic that I will present today is entitled "The WGAN with an infinitely wide generator has no spurious stationary points." This is joint work with Professor Albert No at Hongik University and my students Tae Yoon and Seon Kwon and myself. Let me quickly outline the talk. So first, I'll establish some preliminaries regarding the context and also the analysis of infinitely large neural networks. Then I'll describe the specific WGAN setup that I will be analyzing in this work. And then I'll present the main results of this work. And then I'll show some brief experiments and conclude the first part of my talk. Okay, so first I'll provide some preliminaries. So in deep supervised learning, and I'll be a bit brief with this description for this audience. So in deep supervised learning, one considers the setup with data x1 up to xn. So we assume that we have access to n data points. And we also assume that we have access to corresponding labels y1 up to yn. The canonical example is that xi is an email, is the ith email in the data set, and yi is a label indicating whether the email is a spam email or not. In deep supervised learning, one trains a neural network H, and the neural network H is parameterized by theta. And the purpose of this network is to provide predictions of the corresponding to predictions of the label of the data point X. So in this example, we want the network to be able to take in as input new emails and determine whether those emails are spam or not. The network parameter theta is learned through training. It's learned by the network looking at the training data. Specifically, to train the neural network H, one people in machine learning solves an optimization problem of this form. So this is the average loss, and L is a loss function that penalizes incorrect predictions. So Xi is the ith data point, Yi is the corresponding label of Xi, and then H applied to Xi, this is the prediction of the neural network of what Yi should be. And L is a loss function that penalizes incorrect predictions. So if the prediction is very close to or is exactly the same as the true label, then the network will incur no loss. But if there is a discrepancy between the true label and the predicted label, then the network will incur a loss. And in the training process, we are going to one looks for a parameter theta that reduces the loss on the training data. To perform training, to perform training, or to put it differently, to solve this type of optimization problem in machine learning, people use stochastic gradient descent. So stochastic gradient descent, the vanilla SGD has this form. So we select a random data point and its corresponding random label, and then we evaluate the gradient of the loss function with just that single data point, and then we perform a descent along that gradient direction. In most practical SGD setups, people use not just this vanilla SGD, but some variation of this. So people will use adaptive step size versions. People will use, instead of IID sampling, people will use random shuffling of variations of the index selection. People will also use batch updates, but those are variations to this basic setup. But for the purpose of this talk, I'll be considering the vanilla SGD algorithm. Now, we all know that deep learning has shown remarkable results. So this this approach of setting up a neural network and training it using SGD or one of its variants works remarkably well empirically. But I'm a mathematician, I'm an applied mathematician, so I'm interested in understanding why it is that it works well. It is an undisputed fact that deep learning works well, but why it is that the training works well, why is it that generalization works well, these are unanswered open problems. So in particular, to limit the scope of the problem just a little bit, let's just try to understand why the training works. When does the training converge? And how well does the trained neural network perform in new data? Now, the issue with this, trying to answer this question as is that the analysis of the actual neural networks that people use, bring whatever neural network, the ResNet network or more modern efficient net, whatever network that you can bring, or even the more simple ones like AlexNet, even those ones are just too difficult to analyze. So we understand exactly what happens with the code. We can describe the equations exactly, but it's just not possible. It doesn't seem possible yet, or nobody has figured out how to do so, analyzing these systems as is. Therefore, we need to make simplifying assumptions. We need to somehow, because the problem at hand is too difficult, we need to somehow make certain unrealistic assumptions in order to simplify the problem. And in recent years, the limit in which a neural network becomes infinitely large, in particular infinitely wide, has been intensively studied as a simplifying assumption. The classical line of work along this direction is the random feature learning setup. So in the random feature learning setup, one considers the two-layer neural network. So we can write the two-layer neural network. This is a two-layer fully connected MLP network. And in this setup, we randomly initialize the weights and biases of the hidden layer, say with a Gaussian distribution or whatever random distribution. And then the output layer weights they're randomly initialized, but then the output layer weights are trained from data. The blue weights are not trained, only the red weights are trained. Now, in this simplified setup, training does provably converge, and the trained neural network has a certain generalization performance guarantee. And this line of work was done by Rahimi and Recht in 2008. So this type of result is very old from in a machine learning in the machine learning timescale, and it's now accepted as it's now a classical line of work. Now, recently, though, starting in 2018, so within the past 3 years, there has been further work along this line. And there is actually there's not just one, but several approaches. The two most prominent lines of work are the so-called neural tangent kernel and the mean field regime limit of large neural networks, which I won't describe in detail, but there are two competing ideas. In any case, for both types of works, the story is that when you consider the training dynamics of an infinitely wide neural network, and in this case, we do train all layers, then we can characterize the limit of the network becoming infinitely large as with the so-called mean field regime or the neural tangent kernel regime. And when you do so, you're able to establish convergence guarantees and also generalization guarantees. So in deep learning, what do we want to prove? If we want to prove something, well, we want to prove that if we perform training under this mechanism, the training will work. And we also want to establish that if we train the network in that way, then the network will generalize well to new unseen test data. Well, those two type of results can be established for these infinitely wide networks under using these recent approaches. Now, the common argument for establishing why it is that wide neural networks are easy to train, or that they can be trained with theoretical provable guarantees, is to establish that the loss landscape becomes favorable as the width converges to, the width approaches infinity. So on the left is a visualization of an unfavorable loss landscape. And remember, training corresponds to reducing a certain cost function. So on the left, if we look at this landscape, and if we imagine ourselves as a person standing on these sort of mountainous surfaces, and if we want to go downhill, that may not always be easy because, as you can see, there are many local minima that we might get trapped in if we try to descend this landscape. In contrast, the landscape on the right is much more smooth. There are no local minima. It even looks to be convex. So in this case, getting stuck in a local minima is not going to happen. So the loss landscape on the right suggests that that training on this particular network, this particular setup, would be much more favorable. So the high-level approach is of the prior work is that when the network becomes infinitely large, the landscape becomes something resembling what you see on the right rather than what you see on the left. So what I just described was the deep learning theory analysis of supervised learning for classification problems. And it's actually usually for classification problems where you use the squared loss, not even the cross entropy loss. But the type of learning that I want to analyze, that I want to present in this work are GANs. So let me very briefly explain what GANs are and how it is different from the supervised learning setup. So GAN in particular is an unsupervised learning technique. So GANs, which is short for generative adversarial networks, is a machine learning technique for learning a generative distribution of data. So given data points x1 up to xn, and note that we just have the data, we don't have any corresponding labels. And we assume that this data originates from a certain probability distribution P true. The GAN learns a generative distribution that is in some sense similar to the true distribution. On the left, we can see real images from the true distribution. You can see a frog, a cat, a dog. So these are real images. But the images on the right, from afar, they seem okay. But if you look at them carefully, you can sense that something is a little bit off. And that's because these are actually not real images. These are fake images from the generative distribution that was learned by the GAN. In a GAN, there are two neural networks, a discriminator and a generator. And these two neural networks are trained adversarially by competing against each other. So in this example, the generator is provided as input random noise, and its goal is to generate a fake handwritten digit, and then the discriminator takes in as input some images from the training set. So these are real, true handwritten digits, and then the goal of the discriminator is to discriminate between real and fake images. Then the goal of the generator becomes to generate fake images that are sufficiently realistic enough to fool the discriminator, and the discriminator's goal then becomes to become sufficiently good at distinguishing fake from real so that it does not get fooled. And through this competition, both networks, they grow in their capability, and eventually the generator becomes capable of generating fake images that look realistic even to the human eye. Now, the training of a GAN is different from the training of a supervised learning setup, because in a GAN, to train a GAN, one solves a minimax optimization problem rather than a minimization problem in the context of supervised learning. The solution to a minimax optimization problem is defined as a Nash equilibrium. So theta star, eta star is defined to be a solution if unilaterally changing theta increases the loss value and unilaterally changing eta decreases the loss value. Now, training GANs is difficult, and I mean this in both the theoretical and the empirical sense. So, compared to supervised learning, practitioners report that empirically getting GANs to train is much more finicky. It's much more the parameter tuning is much more delicate. It's hard to get it to work. So, and for this reason, GAN practitioners they speak out for of the need to have a better understanding of the GAN training dynamics, the minimax training dynamics. And theoretically speaking, far fewer results have been established for GANs compared to the supervised learning setup. And in particular, the infinitely wide regime has not been studied before for GANs. And the key technical challenge that makes this difficult is that the interaction between the discriminator network and the generator network is fundamentally nonlinear and non-convex, even in the infinite width regime. Okay, so then let me quickly describe the WGAN setup that I will be analyzing. So when I present work on Minimax optimization or GANs, it's always a little bit, the setup is always a little bit more difficult because there are twice as many parameters, twice as many notation to explain. But let me do so quickly. So this is the architecture. There is the generator, there is the discriminator. In this setup, the generator has a very wide width, or it actually has an infinite width. Both the discriminator and the generator are two-layer neural networks. And if we step through the sort of life cycle of this learning scheme of the PyTorch code, if you imagine, we first randomly initialize the hidden layer features of both the generator and the discriminator networks. Then the output layer weights are trained. So the thetas, the etas, these are the output layer, the final layer weights. And these are trained with data. And then finally, once the training is complete, then in order to use the generator, the discriminator is usually discarded. So we generate a random latent variable, feed it through the generator, and then that out comes a fake image or a fake data point. So for the generator and the discriminator functions, we are both using two-layer, multi-layer perceptrons, two-layer fully connected networks. The generator feature function, the generator function has this form in the finite width setup. In the infinite width setup, we basically just replace the summation with an integral. That's what I mean by an infinite width. And then in the discriminator is not large. The discriminator does not have infinite width, so we just have a finite sum, a regular sum for the discriminator function. And the specific loss that we consider is this loss. So this is the WGAN loss with the Lipschitz constraint on the discriminator replaced with a regular explicit regularizer. And one thing that I want to point out is performing SGD on the minimax problem with respect to the minimax loss function L is equivalent to performing minimization problem with this loss function J. So when I describe the loss landscape, I'll be describing the loss landscape with respect to this J function. Okay, now let me state the landscape results. So our main result is, our first main result is that when we have an infinitely wide generator and a small discriminator, then any stationary point of this neural of this setup is actually a global minimum. So the implication of this result is that when the generator is infinitely wide, then any local minimum is a global minimum. And therefore, the implication is that training will likely converge to the global minimum, since there is no local minimum to get stuck in. The proof technique of this result uses universal approximation theory and techniques from random feature learning. And the idea is actually somewhat distinct from the NTK and the mean field techniques. So that was the infinitely wide setup, but we have also further results. So in the infinitely wide setup, and when we have a large discriminator, we have a similar result, but with a more sort of restrictive condition. I'll sort of skip over this part. And then we also have a finite width result. So when the generator is very large, but not infinitely large, in that case, then we can essentially recover a similar kind of result that we had for the infinite width setup. But now instead of the no local minimum condition holding with probability 1, it only holds with high probability. Okay, now let me show some brief experiments illustrating what the theory is claiming. So the theory, so I think the main result, theorem 1, the first theorem, is nicely illustrated by this landscape visualization. So to get these landscape visualizations, we actually had a sort of mixture of Gaussian setup, and we actually ran some PyTorch experiments. And this is a loss landscape visualization when the generator actually had width 2. And width equals 2 is not super unrealistic because this is a very simple problem. But in any case, the landscape is, as you can see, highly non-convex. There are many local minima that one can get stuck in. And so this is a very unfavorable landscape. But on the right, when the width becomes even just to 10, the landscape becomes much more smoother. And as you can see, there's only one local minima, which is the global minima in this setup. Note that the lost landscape on the right is clearly non-convex. So when I claim that the lost landscape has no spurious local minima, that all local minima are global minima, well, that is what I'm claiming, but I'm not claiming at all that the lost landscape is non-convex. That I'm not claiming that the lost landscape is convex. And indeed, through this example, we can clearly see the non-convexity of the lost landscape. So to conclude my first part of this talk, under suitable assumptions, the lost landscape of a WGAN with a Y generator becomes favorable. And we prove this result using a novel technique based on universal approximation theory. Okay, so that's the end of the first part of my talk. I would be happy to take questions, but I think it's going to be better for me to just finish the talk. So let me move on to the second part of this talk, of my talk. And this part is entitled Accelerated Algorithms for Smooth Convex-Concave Minimax Problems with 1/k² rate on squared gradient norm. So for this part, in the first part of my talk, the simplifying assumption in analyzing minimax training was that the generator network becomes infinitely large. In this part of the talk, the simplifying assumption in analyzing the convergence of the training dynamics is that the training loss is convex-concave, which is indeed an unrealistic assumption, but it's still, in my opinion, a good starting point in terms of the theoretical analysis because this has not been done. Let me outline the talk. So first, I'll provide an introduction and the necessary background. Then I'll present the algorithm that achieves the 1/k² rate as promised in the title. And then I'll present to establishing the optimality of this rate through a matching lower bound. And then finally, I'll present some brief experiments and conclude. Okay, so to put our work in the proper context, let me first describe the prior work on acceleration for minimization problems. So for minimization problems, which would correspond to supervised learning in the context of machine learning, we minimize a function f of x, and we assume that the function f is in some sense smooth, and we assume convexity in this setup. And for this kind of problem, the gradient descent method, the simplest possible optimization algorithm, converges with a rate 1/k. But this 1/k rate is suboptimal, and it actually can be improved. And the way you improve this is through Nesterov's celebrated accelerated gradient method, which has this 2-line description. And this accelerated method, converges with the rate 1/k², which is faster than 1/k. Now, the question that I wish to address in this line of work is, can we provide an accelerated methods for minimax optimization problems? So for minimization problems, Nesterov gave an answer and provided the answer. Nesterov shows us how to accelerate optimization or training in the minimization context. But for minimax optimization problems that arise in, let's say, adversarial training or in the training of GANs, the question was an open problem. So let me describe the problem that we wish to solve. So we will consider the minimax problem with respect to a loss function L. So we minimize with respect to L, we maximize with respect to Y, and we assume that L is convex and concave. So this convex concavity assumption is the simplifying assumption that we use for this line of work. So we define solutions as saddle points, and we'll define the saddle gradient operator as the concatenation of the loss function L with its gradient with respect to L and the gradient with respect to Y, but the sign of the gradient with respect to Y is flipped. By the way, because of the smoothness assumption and because of the convex concavity assumption, a point is a solution, it's a saddle point for this minimax optimization problem, if and only if the gradient mapping outputs a 0. So here are some classical results in minimax optimization. the analog of gradient descent, which is referred to as simultaneous gradient descent ascent, simultaneous gradient ascent descent. This algorithm, which can be written in this form, does not converge in general. So this is not just a sort of theoretical thing. It's understood well by, you can find the counterexample that shows that this algorithm doesn't converge for, let's say, an Ian Goodfellow's GAN tutorial, for example. It's well known in the machine learning community. But this algorithm doesn't converge, but the extra gradient algorithm does converge. So the extra gradient algorithm has this two-line form, and let me describe how the update works. So starting at a current point zk, we evaluate the gradient mapping g at zk, and then step in the negative gradient direction to go to zk plus 1/2. Then at zk plus 1/2, we evaluate the gradient mapping again, but instead of stepping in the negative gradient direction from zk plus 1, we instead return to zk and then perform the step with the gradient evaluated at zk plus 1/2. So we go to zk plus 1, evaluate the gradient there, and then go back and then take the step from zk in order to go to zk plus 1. So I said that the gradient descent ascent method in general doesn't converge, but does EG converge? What does the extra gradient method converge? Well, it does. And here is the convergence, the classical convergence result. So the convergence of EG is usually measured in terms of the duality gap. And the so-called duality gap is a quantity that naturally generalizes the function value that's used in the convex minimization setup. So here's an informal statement of the convergence of EG. So the extra gradient method, the prior work, it converges with rate 1/k on the duality gap. And it's in fact provably optimal. So there exists, so in the optimization literature, it's possible to establish what's called complexity lower bounds, which proves that it's not possible to establish a rate beyond a certain sort of limit. Well, for the extra gradient method, there exists a complexity lower bound stating that this 1/k rate cannot be exceeded. So the conclusion that we take away from this prior work is that the extra gradient method is already optimal when you measure performance in terms of the duality gap, and therefore further acceleration is not possible. Or is it? Well, yes, if we measure performance using the duality gap, then provably extra gradient method is already optimal, so we cannot do any better. But what if we change the optimality measure? And the reason we may want to change the optimality measure is that this thing called the duality gap, it does not generalize really at all to the non-convex, non-concave setup, because the duality gap, the notion of the duality gap, it hinges on the fact that strong duality holds in sort of convex optimization setups. But when you take away convexity, strong duality fails. So this thing called the duality gap doesn't really make sense anymore. And furthermore, the quantity called the duality gap is not something that can be measured throughout the algorithm. When you execute the algorithm, you want to have some quantity that you can look at to make sense of how much progress you're making. The duality gap does not offer such measurable quantity. Therefore, we can consider the squared gradient magnitude of our loss function as the optimality measure. This squared gradient magnitude is something we can measure throughout the execution of the algorithm. And this squared gradient magnitude is something that does generalize meaningfully to the non-convex, non-concave general setup. So is there any prior work that establishes a complexity convergence rate on this optimality measure? And by the way, if the gradient is equal to 0, then that tells us that we are at the solution. So if the gradient is close to 0 but not equal to 0, then we can reasonably conclude that we are in some sense close to a solution. So prior work establishes that the extra gradient method and several other known methods, such as the so-called Popov method, the optimistic gradient method, the stochastic gradient ascent descent with anchoring, these known prior methods exhibit a 1/k rate on the squared gradient magnitude when we use this as the optimality measure. But this rate is not optimal, and we can actually do better. And that's the main contribution of this work. So the main contributions, the two contributions of this work is that we present an algorithm that we refer to as EAG. And this algorithm achieves a 1/k squared rate compared to the prior state of the art, which was 1/k, which is faster. And then the second contribution of this talk is that we established the optimality of this rate with a matching complexity lower bound. So we established that this 1/k squared rate cannot be beat, and therefore this is the optimal rate for this problem class. Okay, so now let me present the algorithm that achieves the accelerated 1/k squared rate. The general form of the algorithm, which we refer to as the extra anchored gradient, EAG, has this form. So it has this two-line expression, and it resembles the extra gradient method in the sense that from ZK, we evaluate the gradient mapping. We go to ZK plus 1, and then we evaluate the gradient mapping again from there, but then we return back to ZK, and then we proceed to move to ZK plus 1. But it differs from EAG. So EAG differs from EG in the sense that it has this additional anchoring term. So this term is the term in the middle is referred to as an anchoring term. So hence the name EAG. And the role of this anchoring term, the purpose of this anchoring term is to figuratively plant an anchor at point Z0 and pull the iterates back towards the starting point Z0. Z0 is the starting point of the iteration. So the anchor pulls the iterates back to its starting points with a certain strength. And the strength at which the anchor pulls the iterates back to the starting point diminishes at rate 1/k. In our work, we present two instantiations of the EAG algorithm. The first instantiation is what we refer to as EAG with constant step size, and we abbreviate it as EAGC. In this setup, for EAGC, the step size alpha k, which used to be alpha k, is no longer iteration dependent. So we just write alpha, instead of alpha k, we just write alpha for the step size. This algorithm converges with a 1/k squared rate with a constant 260. So the EAGC algorithm is simple because the step size alpha is not iteration dependent. But it actually turns out that the analysis is very complicated. So the calculations are actually quite arduous and not at all simple, but we just did it. And the analysis is complicated, but also another issue is that the constant 260 is quite large, and the allowable step size range is somewhat restricted. So in order to address these issues, we also provide another version of the algorithm, another instance of the EAG algorithm, which we refer to as EAG with varying step size, EAGB. So the algorithm now has a iteration-dependent step size alpha, and the step sizes now are defined through this recursive relationship. Now, this algorithm is slightly more complicated than EAGC because of this recursion and because this being alpha k rather than just alpha. So the step size is slightly more complicated, but the analysis is significantly more simpler. And also we achieve a much smaller constant, a constant that's roughly 10 times smaller than what we had before. So we have two versions of a similar kind of algorithm, and we have an interesting trade-off. So we are trading off between the simplicity of the algorithm versus the simplicity of the proof. To quickly outline the proof technique that's being used, the proof is based on a Lyapunov analysis, and it's based on showing that a energy function, a Lyapunov function defined in this way, is non-increasing. So this is the form of the Lyapunov function, and this AK coefficient has to be growing at rate k squared, and showing that this is like an energy. And what I mean by like an energy is that this is a dissipative quantity. It doesn't increase. It decreases or stays the same as the iteration progresses. Showing that is the crux of the proof, and it is actually the hard part. But once we establish that this Vk is a non-increasing quantity, then the remaining analysis is actually rather straightforward. So it's not simple enough for me to describe in this talk, but it is simple enough for me to describe it in these 7 lines of text and equations. So once the energy function is established to be non-increasing, with this few lines of arguments, we can arrive at the convergence result. Okay, now let me describe the, I presented to you the Eag algorithm, which achieves an accelerated 1/k² rate. Now let me present the matching complexity lower bound that establishes that it is in fact optimal, that it is not possible to do better than 1/k². So the main results, the lower bound result states that there exists a difficult instance of a minimax problem satisfying this complexity lower bound, and this complexity lower bound has a constant of 1 and then a 1/k² dependence. And this complexity lower bound applies to any iterative algorithm satisfying this condition. So basically, this type of span condition is something that's commonly used in establishing lower bounds for minimization algorithms. But in this case, we have two conditions rather than one, because in minimax optimization, we have a minimization variable x and a minimization variable y. But otherwise, this is a standard type of restriction that we put in for the class of algorithms. This class of algorithms contains simultaneous gradient methods, alternating gradient descent ascent methods. This contains all the practically used minimax optimization first order algorithms. And the idea behind this complexity lower bound is that is this construction. So the worst case construction is a bilinear saddle function. So L of x, y, the saddle function has this form where x transpose a y, b transpose x, b transpose y. And this A is a symmetric n by n matrix. And the key insight is that the gradient being equal of this saddle function be equal to 0. In other words, finding a saddle point, finding a solution to this minimization minimax problem is equivalent to solving the linear system AX equals B. So, and then what we can do is we can translate the complexity lower bounds on solving the linear system of equations AX equals B, where A is a symmetric matrix, and that comes from some linear algebraic techniques. So since the matrix A is symmetric, and since we're allowed to, without loss of generality, translate the problem so that we start at point 0, then the span conditions that we imposed on the gradient-based algorithm reduces to this, so that the xk and the yk iterate belongs to the k-1th Krylov subspace defined by the matrix A and the vector B. So the idea of Krylov subspaces is and the computational complexity for related to them is a well-studied subject in linear algebra, and in particular, the analysis relies heavily on the use of matrix polynomials. But overall, to summarize the key approach, the key idea is that the bilinear minimax problem generalizes the problem of solving AX equals to B, where A is an n by n symmetric matrix. And for the setup of solving the linear system AX equals B with symmetric A, we have this existing prior complexity lower bound, which was established by Nemirovsky. So it says that to solve AX equals B in the sense of the residual norm squared, it's not possible to do better than 1/k². So with a few lines of arguments, we assume that the starting point is 0 without loss of generality, and then we take the construction that arises from the analysis of the linear system AX equals B, and we plug it in, and that gives us a complexity lower bound for making the gradient small for the minimax loss function of L, and in particular, we have the lower bound 1/k². Okay, so let me show you some brief experiments and conclude this talk. So we ran the Eag algorithm and other existing algorithms to solve minimax problems on some simple synthetic problems. And as you can see here, so this is actually two curves on top of each other. So both EAGV and EAGC and EAGV converges as a rate 1/k², because this blue dotted line is the guideline that indicates the convergence rate 1/k². Whereas the prior algorithms, the simultaneous gradient descent ascent with anchoring, with the extra gradient method, the Popov algorithm, they do converge, but they converge at the rate 1/k, or actually it's a rate 1/k. On the right, this is an illustration of the trajectories of the various algorithms applied to this this particular problem. And as you can see, the red line is the extra gradient algorithm, the prior algorithm, and it does converge to the solution, which is at the origin, but it has this cycling behavior. And it is this cycling behavior that represents the worst case in minimax optimization. The EAG algorithm, due to the presence of its anchoring term, it can essentially avoid the cycling behavior, and the anchoring term serves as allows the iteration to the cycling behavior to be dampened out and allows the iteration to converge to the origin, to the solution, much more directly and much more quickly. Okay, so let me conclude the second part of this talk. So with the extra anchored gradient method and a matching lower bound, we established the optimal accelerated 1/k squared complexity on reducing the squared gradient magnitude for smooth convex concave minimax problems. And an observation that I wish to make is that although the overall form of the results of this acceleration is similar to the prior acceleration of Nesterov. So both Nesterov and this acceleration reduces the standard 1/k rate, improves the 1/k rate to 1/k squared. So there is a similarity in that regard, but the mechanism seems to be entirely different. So Nesterov's acceleration relies on the use of momentum, which is used widely throughout deep learning training. Whereas in our EAG method, the key mechanism seems to be the anchoring term, which in some sense feels kind of the opposite thing of momentum. But I wonder if these two acceleration mechanisms are entirely unrelated, because at a surface level, they seem unrelated, but it would be surprising to me that they are indeed entirely unrelated. I expect there to be some non-obvious connection between them, and that's something I would like to know. Okay, so that's the end. All right, so that's the end of the second part of the talk, and that concludes my talk today. Thank you, and I can take any questions.